Hi everybody. Today I am recording the final lecture for dynamics. The last lecture will be a brief overview of section 18.2 in our textbook, and I've decided to omit the rest of chapter 18. So the first thing I want to show you is I'm going to change this up a little bit so that this will be called lecture number 30 that I'm doing today. And I will also edit this to let you know that this is the last new material for the class. So I wanted to show you this because I did not want you to be confused since we had talked about doing this a little bit differently. So I'm deleting lecture 31. That makes lecture 30 and section 18.2 the last new material. That also means that when you look at submit homework for chapter 18, what you'll see is there are only 3 problems. And so I'm going to specify that this is the second and final problem set. So there are not 3 problem sets, but there are only 2 with a total of 3 problems. So just to clarify that, I wanted to make sure that we were all on the same page as far as the web page. So that's kind of redundant, but there you go. So the next thing I want to do is to talk to you about the PowerPoints for chapter 18. The last PowerPoint that we'll cover is number 25. So everything 26, 27, down to 31, which talk about different types of motion, starting with the gyroscope, is not going to be covered in this course. So if you are interested in that, section 18.3 is I would say a difficult read, but it's also very interesting. So keep those things in mind if you want to work that out. So for those of you that were in lecture before Thanksgiving holiday, we had talked about the material about the angular momentum 2 lectures before, and then in our last lecture together we talked about motion of a rigid body in 3 dimensions. So this is just a very short rehash of that if you were in class, and if not, then you'll be able to see this for the first time. So anyway, when we take into account the angular momentum and rate of change with respect to a centroidal axis, that means centroidal, in other words, attached to the centroid of a 3-dimensional rigid body, we can create a transformation of omega, or the angular speed, into angular momentum, and it will be independent of the coordinate system. So in the same way that the force, summation of forces is equal to mass times acceleration, the summation of moments is equal to the rate of change of angular momentum when it's about the center of gravity, or the center of mass. So it's convenient to use fixed body axes, which would be G, X, Y, Z, all right, where the moments and the products of inertia are not time dependent. And when we look at it that way, we can define the rate of change of angular momentum with respect by breaking it into those 3-dimensional vectors. Now I want to eliminate this so that you'll be able to see we're talking about big omega is in this case equal to omega, the angular momentum, or excuse me, the angular velocity. Right. So if we continue down to the next page, it was just arguing with me a little bit there. We have Eulers Equation of motion and D'Alembert's principle, which just have to do with changing those axes. And let's get this one up so we can see it. So when we think about capital omega equaling little omega and that fixed set of axes, we can then talk about the summation of moments equals the rate of angular momentum change of the center of gravity, or about the center of gravity with respect to the fixed axes, plus big omega crossed with h sub g. So what that really does is it takes us from a fixed axis system to a rotational or to a general axis system. At that point, Euler's equations can be expressed in vectors. And remember, the big thing is when we're talking about rotation in 3 dimensions, what the big change from what we're doing before is we have to really be careful of our vectors. We have to be rigorous about breaking things into all 3 coordinate directions. When we have something in 2 dimensions, we can really work just with things in 2 dimensions and then realize that all of our rotational stuff is in the 3rd dimension, so it greatly simplifies the math, but the principle is exactly the same. So the upshot of this is the system of external forces and effective forces are equivalent for general 3-dimensional motion. So in other words, it's just the same. And the system of external forces are, let me get rid of this, are equivalent to the vector and the couple m times a, which of course is the acceleration of that mass center, and the vector h sub g. All right, so we just break that down a little bit more, and we're just setting up these equipolant systems, and eventually we get to this where we just have the 2 vectors. We have the mass times the acceleration of the mass center and the angular momentum, the rate of change of angular momentum about the mass center being equal to that system of the moments that are created by the external forces. So once again, it's exactly the same as in 2 dimensions, just that we now have to be just a little bit more rigorous about our vector math. All right, so when we have, there, I want to get everything up here on the slide. I'm not crazy about keeping the hidden stuff. But so for rigid body rotating about a fixed point, we're going to have a little bit of a simplification. When it's rotating about a fixed axis, we're going to have to expand those equations. Let me pull this down so you can see the bottom of that. There we go. And so we're going to have a little bit more vector math. We just need to be more rigorous with our dimensions, but the conversation is exactly the same. All right, so this just continues that discussion. And when we are talking about a rigid axis or rotation about a fixed axis, we just have to, these are just 2 simplifying assumptions. If it is symmetrical with a plane, we can view it this way, and if it's not symmetrical, the sum of external moments will not be 0, even if alpha is equal to 0. So we'll have to include all of those in our conversation. All right, so if you have a rotating shaft, which is just an example of this, where omega, where omega is equal to 0, meaning it's static or sitting still, and dynamic, where it's not equal to 0, it requires balancing both to avoid excessive vibration and bearing reaction. So that's like an application for this. And then sample problem 18 just gives you a shot at looking at how this works. Right? So this will be handled, you'll be able to look at something very similar to this in the last homework problem, which I believe is 18.56. But it will talk about this and you'll be able to work through the math. So intuitively, this can be a little difficult, but my advice to you when you're working this problem is to just be very, very rigorous with your math, to keep in mind all of your vector directions, to try to visualize it conceptually at the beginning, but then really rely heavily on the directional properties of the vectors and work through the math, and everything will turn out fine. But the problems are lengthy, so make sure that you allocate some time. That's why you only have 1 problem for your homework on this material. All right, so here we just have some of the ideas. We just work through that. We get the acceleration, we get the angular momentum, we get the rate of change of angular momentum, and everything, as you can see, is broken down vectorially, ijk, and it simplifies at the end, but we don't look for the simplification right off the bat. All right, and then we can express that the system of external forces is equivalent to the system of effective forces and write vector expressions for those sums of those moments. And that takes care of all of the material in this chapter, and that is the last piece of material that we're going to have for this class. So after you finish the homework assignment for chapter 18, which is just those 3 problems, but they're very lengthy problems, especially the last one, then we'll be ready to prepare for the final exam. So in our remaining time together, we'll review this work. If you have questions or problems, if you're in class, please bring those to my attention. If you're not in class, please email me or request a Zoom meeting. We can work together to get your stuff done. And then final exam in 2019 is no later than December 13th. So if you're watching this in a different year, we will have a different schedule, which will be clearly enumerated on our Moodle page. But please, the most important thing is let me know when I can help you, and we will finish the class, hopefully with great success. So thanks, everybody.